Good afternoon, everyone. We are learning the subject of electromagnetics. In this subject, we are learning the chapter of the radiation. Today, we will simplify the few numerical on the basis of the radiation. So, we will simplify the numerical on the basis of the electromagnetic radiations. Start with the numerical number 1. Note on the numerical. Number 1, a short antenna with a uniform current distribution. A short antenna with a uniform current distribution in a free space has ITL is equals to 3 into 10 raised to the power minus 4 ampere meter. First of calculate mod of E theta. Calculate mod of E theta for theta is equals to 90 degree and phi is equals to 0 degree. If the lambda is equals to 10 centimeter and the radius r is equals to 200 centimeter, assuming for the field components. First off. So by looking this numerical, we can understand ourselves as this numerical is totally related on the electromagnetic radiations. Okay, and that to application of the transmission line and the antenna, transmitting and the receiving at the transmitting as well as the receiving antenna, and the coordinate system which we are going to continue in this case is nothing but the spherical coordinate system. How we can identify it? Just by looking the parameters. Already we have studied in the unit number 1 in the vectors. The x, y and the z are nothing but the Cartesian coordinate system, whereas rho, phi and z are nothing but the cylindrical coordinate system, whereas your r, theta, phi is nothing but the spherical coordinate system. So see here the theta is a 90 degree, phi is a 0 degree, and the r radius is given. So in this way we can say this is nothing if we are interested to find out the radiation of the antenna in the spherical coordinate system. So how we can simplify this one? All the expressions are already derived expressions. Only we need to substitute the values and we need to get that answer. So here for simplifying this numerical, we need to find out the electric field at a particular directions. Okay, then later on we can find the rest of the thing, that is nothing but the what we can say E at the theta. First of all, we should calculate that is the E, because we know very well E is nothing but the electric field intensity. Or how we can write that expression, or you can say the equation in the vector form of that electric field. E is equals to, especially in the spherical coordinate system. So E will be equals to ER AR plus E theta A theta plus A phi A phi likewise. Okay. So here we mentioned clearly for the far field zone means the distance is too far, and at the time we are interested to find out the electric field intensity at a particular direction, that is nothing but the A theta directions. Okay, so how we can simplify? Electric field is equals to IDL sin theta divided by 4 pi omega epsilon 0, and the exponential form is nothing but e raised to the power j beta r. Why this r apostrophe is of r? Because we are interested in the radius at this moment. In this way, j beta square divided by r of a theta. So this part, especially this part, is related to the a theta. By concentrating, by focusing on that in the direction of a theta, we are writing this expression. So ID is given is here the 3 into 10 raised to the power minus 4. Theta is also given. Phi is also given. The radius r is also given. Even the wavelength, that is a 10 centimeter, is given. So just substitute one by one here. So what will happen? So the expression, this part will be the as it is. Okay, this part will be the as it is. What is the beta? What we need to substitute at the place of the beta, that is too important here. Okay, what we need to substitute at the place of beta. So the beta will be equals to, how we can find that beta will be equals to your omega root of mu 0 epsilon 0. Okay, so this the formulas already we have studied, learned in the uniform plane view also. Okay, and in many places. So beta is nothing but the phase constant is equals to omega is nothing but the angular frequency. Root of mu 0 epsilon 0 is nothing but the permittivity and permeability at a free space. So by substituting this value of your the mu 0 and epsilon 0, you can conclude that is nothing but your the beta is equals to 2 pi by lambda. Okay. After calculating these things, we can get finally that in the other way, you can say that is beta is nothing but 2 pi by lambda is also another way you can calculate that the phase constant. Now substitute the value here. How you can substitute the value at one place with respect to the r, you can 2 pi by lambda you can place, and directly in many of the cases if you are going to consider in the exponential form, at that time beta is nothing but omega root of mu 0 epsilon 0. Okay, so here the real and the imaginary two parts are there. The what because the imaginary part is nothing but denoted by this j just get it at the outside. Okay, and simplify the this previous e raised to the power. If you're going to simplify that one, so you will get jb back outside, and the idl sine theta 4 pi epsilon 0 omega and omega of root of mu 0 epsilon 0 2 pi by lambda r of a theta. So see here, so ideal is already given here. The omega is nothing but the 2 pi f, and this part is nothing but we can write in terms of the intrinsic impedance. Also many things will cut out. This omega will cancel out. Okay, and this lambda by r and the 2 pi will be as it is, and this root of what we can say mu 0 epsilon 0 we can write in terms of here the what we can say, because here is also mu 0. See here, this omega is going to cancel out, no doubt at all. But if you observe this ideal sine theta divided by 4 pi, and this mu epsilon 0, and this in the numerator root of mu 0 epsilon 0 divided by this epsilon 0, if you are going to simplify, you will get the intrinsic impedance at a free space is nothing but the eta. Okay, so in this way, this term entirely root mu 0 epsilon 0 divided by epsilon 0 is nothing but the eta 2 pi by lambda r will be as it is. Now substitute the value whatever they given. This expression is ideal. Okay, ideal you just keep later on you just divide these parameters. Okay, after dividing this parameter and substituting the value, so you will get as, why we are taking this 60 pi, why we are taking this 60 pi, so we can get this as 60 pi expression just because we are considering in the a theta direction. So here will be the division, even though that is a theta is given as a 90 degree. Okay, theta is given as a 90 degree, but that 90 degree again and this what we can say this 2 pi will be multiplied with that also, then they divide with the 4, so you will get this part. So in this way the magnitude of that particular component of electric field you can get, that is mod of E is equals to mod of E theta. So in this way this final you will get after reducing this expression you will get sine theta divided by r. Now substitute this 60 pi will be outside, and the idea is nothing but 3 into 10 raised to the power minus 4, and these values substitute the value of r, substitute the value of theta, substitute the value of the lambda. So finally you will get as the electric field intensity at a particular a theta direction is nothing but 0.2827 and measured in volt per meter. Measured in volt per meter. Next, the radiation resistance of an antenna is 72 ohm and the loss resistance is of 8 ohm. What is the directivity if the power gain is 30? What is the directivity if the power gain is 30? So in this case, what we need to calculate? We need to calculate the directivity of the gain. Okay, which parameters is given? See here, the radiation resistance is given. The lossy what we can say the resistance is given, and we need to find out the directivity if the power gain is also given, that is nothing but the 30. So how we can start that one, the directivity or you can say the maximum directivity gain can be get with the help of the what we can say the by finding that directivity gain. Okay, and that is possible with the help of the efficiency, and the efficiency is possible with the help of again the power gain. Okay, so power gain can be calculated by substituting the final efficiency. So in this way, we can start indirectly with the finding the efficiency of the antenna. Okay. So here the efficiency of the antenna can be written or can be found. The radiated efficiency or the what we can say the receiving antenna efficiency is equals to P radiated, that is the power radiated divided by radiated power plus loss of that power. Okay, so how we can find this loss of power, that we need to convert in terms of the all this power we need to convert in terms of the resistance, because that is given directly. So this power, radiated power, will be nothing but here the radiated resistance. Again, this is again the radiated resistance, and this is nothing but the loss of resistance. So what is given, this entire power form will converted into this register, just because of the values are given in that form. So 72 divided by 72 plus 8, here will be 80, that is nothing but 90% of efficiency we are getting at the receiving point, okay, radiated efficiency. So here the power gain of the antenna can be given by, so the maximum power gain, this max max is nothing but the max P is nothing but the power, capital G is nothing but the gain. So maximum power gain can be determined as efficiency with the maximum directivity gain, with the maximum directivity gain. So how we can find this maximum directivity gain? So maximum directivity gain can be calculated as P max divided by the in what we can say the eta, that is the intrinsic impedance. So here will be your the 30, which is given power gain. So 30 divided by 0.9, so you will get 33.33. Okay. Now next is nothing but how we can find the directivity in terms of the dBs, because we know very well the directivity gain is measured in the decibel. So that is the GD, what we say the GD max in terms of the dB can be calculated as a 10 log 10 of GD max. So 10 log 10 of what you got without dB, that is nothing but 33.33. So 10 log 10 of 33.33 will be equals to 15.228 of in terms of the dB. 15.228 is in the dB. So always remember, if not given, even though not written, you need to find out in the dB and all, but always end with the dB, because directivity gain is measured in the dB. Calculate the radiation resistance of lambda by 10 wire dipole in the free space. There are various kinds of dipole, that is a half dipole, wire dipole, twisted, and many more. So in this way, here particular question mention here, calculate the radiated resistance, that is nothing but R radiated. Okay, if the valence is given, that is nothing but lambda by 10. Okay, and which particular dipole is used here? Wire dipole is used in the free space. So how we can calculate that one? So directly the formula expression related to that is nothing but the radiated resistance of the antenna is given by R radiated is equals to 80 pi square dl by lambda bracket of whole square. So here the antenna length or the differential length of that antenna is nothing but pi by, oh sorry, lambda by 10 is given already. So dl is nothing but lambda by 10, which is given. So you can substitute in the formula. Radiated resistance is equals to 80 pi square in bracket. What is the dl? dl is a lambda by 10 divided by again the lambda of bracket of whole square. So how that lambda will cancel out, how the 10 square, then the 80, then the pi square. So you will get finally 7.8956 ohm that you are going to measure your radiated resistance. Okay. So this radiated resistance you are going to measure for the antenna radiation. Next is nothing but find the current required to radiate. Find the current required to radiate a power of 100 watt, a power of 100 watt at 100 megahertz, from a 0.01 meter Hertz dipole, from a 0.01 meters of Hertz dipole. This is a particular dipole of a scientific name that scientist is given the expression to find out that dipole in that in the antennas while you are going to measure the radiations. So here the find the current required to radiate the power. We are interested here to calculate the current. What is given? The radiated power is 100 watt is given with a frequency of 100 megahertz, and that too the A part is the parameters or the dimensions, you can say the elements is nothing but 0.01 meter is given. So in the free space, the velocity of light, in many of the textbooks, they are velocity is representing the V or the C. They depending upon the textbook or author, they are using either the V or the C. Is a 3 into 10 to the power 8 meter per second. The power is radiated in the free space at a particular frequency is 100 megahertz. So how we can find that wavelength is we can find the wavelength. How it is possible to find out that wavelength? To find out that current. Okay, so that lambda is nothing but the c by f. C is nothing but again the velocity of the light, 3 into 10 to the power 8 divided by f is nothing but the 100 into 10 to the omega is that is nothing but the 6. So in this way you will get the wavelength is the 3 meters. Similarly, the power radiated in terms of the RMS current is given by the P radiated is equals to 80 pi square d hour divided by lambda of bracket of whole square into I square RMS. So I RMS value of square. So here to calculate that I RMS value, the other parameter must be known. So P radiated is we are having DL, we are having the wavelength, we are having now it is easily we can find the other parameters. So what is that? P radiated is 180 per square will be as it is, and your the DL is nothing but 0.01 is given, and the lambda is nothing but wavelength is the 3 of whole square, and the unknown parameter is nothing but your the IRMS square. So this IRMS you just take at one side, so 100 divided by this entire term 80 pi square of your the 3 divided by 0.01. 0.01 of whole square. So in this way you can calculate the final IRMS value is nothing but 106.76 ampere. That the current we are finding the particular current or radiated current is nothing but 106.76 ampere. Now go for the next. An antenna receives a maximum power of a 2 microwatt. An antenna receives a maximum power of a 2 microwatt from a radio station. Calculate its maximum effective area. Calculate its maximum effective area if the antenna is located in the far field. If the antenna is located in the far field of the station, where mod of E is equals to 50 millivolt per meter, where the mod of E is equals to 50 millivolt per meter. So here the maximum power received is PR max, that is a maximum power received. Okay, maximum power received by the antenna is nothing but 2 microwatt is given. So average power density is given by P average. This type of numerical we have simplified in the uniform plane below in the finding the Poynting vector theorems. So we have calculated the P average is equals to 1 by 2 mod of the electric field intensity divided by the intrinsic impedance. So 1 by 2, this E is the given here the 50 millivolt. Okay, so 50 into 10 to the power minus 3 of whole square divided by eta is nothing but 120 pi. So in this way we can calculate. We are having the value of E, we are having the value of eta. So in this way we can calculate the P average. Okay, average power 3.315 microwatt. So in this way we can find the unknown parameter, that is nothing but the effective aperture area of your the antenna can be calculated. AEM, that is the maximum effective aperture. AEM. A is the effective aperture, or AEM is nothing but maximum effective aperture. That can be calculated as PR max divided by P average. That is the maximum what we can say the radiated resistance power is equals to 2 into 10 to the power minus 6 divided by 3.315 into 10 to the power minus 6. So these two will cancel out, 10 to the power minus 6 and 2 divided by 3.315 is nothing but 0.6033 meters square. 0.6033 meter square is nothing but your the maximum effective area, or you can say the maximum effective aperture. Go for the next. Determine the magnitude of the electric as well as the magnetic field, that is nothing but the E and the H. E and the H of a half wave dipole operated at a frequency of 300 megahertz at a distance of your the 100 meters in the broadside plane for a maximum radiation. The input current to the antenna is 100 angle of 0 degree milliampere. To stop, how much average power is radiated by this antenna? Okay, so here we need to determine the two magnitudes. One is known as your the electric field, other is known as your the magnetic field of your the half wave dipole. The frequency is given, that is a 300 megahertz. The distance is given, that is a 100 meters. Okay, and the current of that antenna is given 100 angle of 0 degree. Okay, so we need to find the that magnitudes of E and the H. So just note on here the given parameter, that is nothing but the I is given 100 angle of 0 degree. So the what we can say, the mean or the peak or the maximum current is nothing but here the 100 milliampere is given. Fine. And the next is nothing but what is mentioned here. The broad plane means the maximum radiated, that is theta. Okay, so in the angle, that is nothing but the broad plane, for especially for the maximum radiation. How we can get that maximum radiation at a particular angle, that is nothing but the 90 degree. At a particular 90 degree we can get the maximum radiation. So okay, and the magnitude of the electric field can be calculated as. So this already in especially in the what we can say, the at a particular direction, that is nothing but the E theta, while we are going to simplify the E as well as H. Once you got either the E or the H with the help of this formula, that is intrinsic impedance is equals to E by H. Intrinsic impedance is equals to E by H. So one of the two parameters is known, because this is the constant value we can get directly, but from the E and the H, if one of the known, the other you can calculate easily. So first of all, we will start with the finding the electric field at theta. So E theta is given, and this is also the derived expression. So for you people, there is no derivation. So directly you just note down here mod of why we are taking mod. If there is a negative sign is there, that can you can avoid and neglect. Okay, so E theta, mod of E theta is equal to 60 Im by R. So cos of pi by 2 into cos theta divided by sin theta. So here 60, what is my Im? The maximum current is nothing but 100 into 10 power minus 3. Or we got this 100 we got the magnitude of that particular direction. So cos of this pi by 2, and again that with a 90 degree. Okay, and sine of 90 degree, because at particular 90 degree the maximum radiation we can get. So after substituting all these things, we got here the mod of E theta is nothing but the 60 millivolt per meter. 60 millivolt per meter. Now just for finding the H, that is a magnetic field intensity. So mod of H, you may increase one of the step, that is eta is equals to E by H. Eta is equals to E by H. So here the H is equals to E by eta. So here E is nothing but 16 into 10 to the power minus 3 divided by 125. Substitute the value 159.15 microampere per meter. So ampere per meter is nothing but the unit of the magnetic field. Volt per meter is nothing but the unit of electric field. So later on, what is the case? That is for the half wave dipole, how we can find the radiated resistance. That is nothing but the, with the help of the expression we are aware, that is a 73 is a radiated resistance. So hence the average power uh, can be given as the average power can be found with the help of this radiated power. Okay, with the help of this radiated power, how we can find the remaining part? That is nothing but the average power is equals to radiated P is equals to I square R formula. The average power can be calculated as P average is equals to I square R. So what is I square? IRMS square into R radiated. R radiated for the what you can say, the dipole is 73, and the IRMS square that is given. So Im by root 2. So what is the Im? Im is 100 milliampere. So 100 into 10 to the power minus 3 divided by root 2 of a whole square. So IRMS is equals to Im by root 2. You can substitute the value, you will get the average power is 0.365 watt. Go for the next. A lossless quarter wave monopole antenna is situated above perfectly conducting the ground plane, and it is driven from the 300 megahertz source with the amplitude of 100 volt. Calculate the average power radiated if the antenna impedance is 36.5 plus J of 21.25 ohm, and internal resistance of source is a 50 ohm. So by looking this figure is given in the numerical, that is one resistance of a 50 ohm with the source of here the 10 volt at a frequency of 300 megahertz with a monopole. The internal resistance of that monopole antenna is nothing but given in the rectangular form, that is 36.5 plus J of 21.25 ohm. So how we can simplify this one? By looking at the figure, we can apply what we can say, the loop, and we can find how the after applying the source, how the current will start to flow, how we can find that the closed loop current. Okay, so by applying the KVL to the circuitry, V minus IR is equals to 0. V minus IR is equals to 0 in that particular loop. So here the V is given here, V is equals to, no, later on V minus IR is equals to 0. So V is equals to IR. So what is the V? V is 100. IR is given here. IR, that is a I into 50. And again the IR is in the rectangular form, is nothing but the 36.5 plus J of 21.55. So in this way, you just add this magnitude, you will get 86.5, and the imaginary part is a 21.55. Likewise, you can get the current answer. I is equals to V by R. So V is 100 divided by R is this rectangular form. So that you just convert this rectangular form 86.5 plus 21.55 J of 21.55, convert into the polar form. So you will get the 100 divided by so and so in the magnitude angle of theta 1 minus theta 2. So 0 minus of this, whatever you will get as 31.86. So in this way, the magnitude will be the 1.122 and the angle is minus 13.8 ampere. So hence the average power radiated is given by P average is equals to I square R. So what is the I? I is IRMS, that you can write IM by root 2, and the R radiated will be as it is. So substitute the value of R radiated to 36.5. What is the IM? 1.122 root of 2 of a bracket of whole square. You will get 23.0065. Go for the last numerical. A half-wave dipole is a lambda by 15 meter long. If its loss resistance is 1.5 ohm, calculate the radiated resistance RR and the antenna efficiency. So here the half-wave dipole is given of a wavelength of that is nothing but the DL lambda by 15 is given in the meters. And secondly, you are the what we can say the resistance loss is nothing but the 1.5 ohm. You need to calculate the RR, you need to calculate the efficiency of your the antenna. So how we can calculate if the given two parameters are given? The given DL is equals to lambda by 15 meter and the loss resistance is 1.5 ohm. So radiated resistance of the antenna is given by R radiated is equals to 80 pi square DL by lambda of whole square. Okay, always be remembered careful about the which dipole is given, wired, half wave dipole and other antenna. Accordingly, the formula will be there. So radiated power is equals to 85 square DL by lambda whole square. Substitute the value of here the DL lambda and the parameter radiated, you will get 3.509 ohm. How we can find the efficiency of the antenna? The antenna efficiency can be calculated. Eta is equals to radiated resistance divided by radiated resistance plus loss of resistance. So here 3.5091 and 3.5091 plus 1.5, you will get 0.7005. So in terms of the percent, you can get as regards the 70.05% or simply on an average 70% is nothing but your the antenna efficiency. So in this way, we have tried to simplify the full numerical, which is on the basis of the electromagnetic radiations. So depending upon the type of the antenna, depending upon the parameter which is given, depending upon the given parameter and the funding parameter, we need to simplify the numerical. We need to remember the expressions. We need to remember the expression. We need to remember the units. We need to remember the formulas and all, so that it will be easy to simplify all the numericals which are related to the radiations. So in this way, I'm going to end the session. Thank you so much.